I'm going to talk to you a little bit about sort of the research that really formed the core of my research career. I still keep up with this stuff. And the main thing I want you to notice here is the large number of people involved in doing scientific research. It's another reason for really not just being a math and science nerd, you know. There's this really, people envision scientists as living in dark, you know, labs with their lab coats, and the Big Bang Theory doesn't do anything to help our image. It really, you have to be able to work with people, because everything today is teamwork. And so I basically studied galaxy evolution in 3 parts. I tried to study the very, very distant galaxies when the first galaxies formed. We can do that very well with telescopes like ALMA and Hubble and Spitzer. You can study then nearby galaxies because that tells you what the universe is today. And then you can study galaxies that are very small, like the Large and Small Magellanic Clouds, the nearest galaxies to the Milky Way, that you can see from the southern hemisphere, and those are probably still in the process of forming today. And so my goal is really to piece together a storyline to try to understand how galaxies form. So I always like starting with this slide. This slide comes from an old old road map that was devised and run by Ellen Dressler called Cosmic Origins. And what this picture shows you is the jigsaw puzzle of the universe. This jigsaw puzzle is really a jigsaw puzzle from the Big Bang to the formation of the first galaxies and stars to ultimately, you know, formation of planetary systems. At some point, Earth formed, our solar system formed, and life came into existence. And whether you're a chemist, a biologist, a geologist, an astronomer, or a physicist, all of us really are interested in piecing together all the pieces of this jigsaw puzzle. So it doesn't matter to me what kind of science you do, because we all want to put this puzzle together because we want to figure out why we are here, what is our place in the cosmos, and how does it all fit together. I also joke that this shows you the funding priorities with very little money going into astronomy and lots going to life sciences, but that's just a joke. It's not really true. What it really reflects is how much more we know because we live on the planet Earth and because we can explore our own solar system. We know a lot more about life processes on the Earth and very little about the first processes, the first evolutionary processes of how the first galaxies formed, how stars formed, and how planets formed. And even today, even though we roughly know how stars formed and how galaxies formed, the moment of star formation is just magic. We know at some point gravity wins, and you have nuclear fusion in the center, and stars are born. You know, but we don't really fully understand how galaxies come together, how baryons separate from dark matter, and it will take us, you know, millennia to figure these big questions out. But we're starting. And my focus is always has been on understanding galaxy formation and how the first galaxies formed and evolved to look the way they do today. In reality, we have a zoo of galaxies. And roughly speaking, as you all probably have heard of the Hubble sequence, we can divide them into sort of 2 or 3 broad categories. We have elliptical galaxies, which are often called old, red, and dead galaxies. They look like either footballs or soccer balls. They have very little dust in them. They're made up of stars that are usually believed to be quite old. And I will not be talking about, although I can mention to you what we know, when and how these formed. Now, the right-hand side of this picture are the disk galaxies, the beautiful spiral arms that you see in these galaxies. And these are the kinds of galaxies that we're all familiar with. They have lots of blue arms because stars are forming in them. All of these galaxies have a black hole at the center. And we're trying to understand how this Hubble sequence came together. Now, if you're really sharp-eyed, you will see in the bottom, there are these galaxies with this ruler-like rectangular structure in the center. And that's a bar. It turns out that even though everybody thinks of this as a typical galaxy, these bar galaxies are more common and more numerous amongst the disk galaxies. 2/3 of all disk galaxies today are barred spiral galaxies. You know, and so that's really what got my attention when I was a graduate student. That's why I started studying barred galaxies. and really specialized in understanding barred galaxies. And as I'll show you, these bars are important evolutionary signposts of the age and maturity of a galaxy disk. And they give us very important information on when a galaxy must have formed and become an adult. Now these galaxies on the right, irregular galaxies, are very common, and they're probably still evolving. Some of them do have a bar, they will eventually form a bar, but I won't talk about those either. I'm going to step back for a second and just remind you of this beautiful picture that came out in 1995, which I think it made the New York Times and every other paper. It was a very deep 100-hour observation taken with the Hubble Space Telescope and the Big 2 camera. And what we told people at the time, which blew everybody's mind, is that every single point of light that you see in this picture is a galaxy. Right? Our own Milky Way has 100 to 400 billion stars, and our universe is 100 to 400 billion galaxies. And the more you look, the more galaxies you see, and they're distributed as elliptical disks or irregular galaxies, as I just showed you. And this is the picture as of 10 years ago, still the deepest picture taken with Hubble, 100 orbits with the advanced camera for survey. And again, every single picture, every single thing you see here is a galaxy, except for a star here and here that you can see. And you can tell those are stars because of the diffraction patterns from the telescope itself. This is the Hubble sequence. So Hubble in 1920s wrote a paper in Astrophysical Journal called the Hubble tuning fork diagram. He put elliptical galaxies on the left, spiral galaxies without a bar on the top, which he called normal galaxies, and these deviant abnormal galaxies called barred galaxies he put on the bottom. Just like then, as now, books are what sell. In 1936, he published a book called The Realm of Nebulae, which was far more popular than his paper. And so that's what made the Hubble sequence, the tuning fork diagram, popular and became part of people's vernacular. And this tuning fork diagram was often envisioned by early astronomers as a way how galaxies might have evolved. And they were trying to figure out whether galaxies evolved this way or this way, and there's a lot of back and forth. And it turned out, at some point people said, no, this doesn't tell you anything about how galaxies evolved. And that was largely true for a long time. Astronomers also like giving names to categories, so they would call the left side of this tuning fork diagram for spiral galaxies early type galaxies, and the right-hand side they would call late type galaxies. And that's worthwhile for you to know. As you read more articles, you will see people call something an early type or late type object. Now, normally, early and late type doesn't always relate to age. So again, we make things confusing because we like our job security. But in reality, there are very different reasons why people call something early type and late type. But just so you know, early type galaxies, which are here, let's ignore the right-hand side, okay? We're not going to talk about elliptical galaxies, which are very, very early types. But we'll call these early type galaxies are characterized by a very big bulge in the center that looks like an elliptical galaxy. And it has spiral arms that are very, very tightly wound. You know, they almost come back on themselves. In the late type galaxies, the nucleus is small, very tiny, and the spiral arms are very loosely wound. These galaxies also tend to get bluer as you go to the right, and they're redder as you go towards the center. And even though for a long time astronomers didn't believe that this had anything to do with age, I'll actually show you that this is one of the rare cases where when we call something early type, it actually ended up being early. And late types actually ended up being late. In that they came early into adulthood as the universe aged, and these guys are late into adulthood, and they're newer galaxies in some sense. Okay, and I'll try to convince you that that's the case. Okay, so Hubble called these galaxies normal galaxies, and these galaxies barred galaxies, but it turns out that these galaxies are in fact the more normal disk galaxies in the nearby universe. And these barred galaxies, as I told you, are 2/3 of all disk galaxies in the nearby universe. So these disks are incredibly thin, right? Our Milky Way is a spiral galaxy, and in fact is a barred spiral galaxy. We live 8 kiloparsecs, or 25,000 light years, from the center of the galaxy. The bar in the center of our galaxy looks like that, is about half the distance from us to the center. So the bar has a length that would be 12,000 plus 12,000, 25,000 light years in length. But we are 25,000 light years from the center, so it's about half the radius. This is the center of the galaxy. The bar is like this, and we are out here, twice as far. Imagine a very, very thin disk, like a record player, you know, in the old days, the record disc. That's how thin galaxies are, right? They're extremely thin objects. The bar is also very, very thin. Imagine a toothpaste box that you squeeze down. That's what a bar is like. So it's rectangular, like those TIE fighters in Star Wars, and usually has spiral arms coming out from the end of the bar. This overdensity of stars that is in the center is a natural outcome of galaxy dynamics. And over time, we believe that every galaxy should form a bar, and I'll show you a simulation of this in a second. Today, 2/3 of these galaxies, including our own Milky Way, have a bar in the center, and the bar is characterized by these two dust lanes that you see on the leading side of the bar. Now, we always assume in astronomy that spiral arms are trailing, and that's telling you the way in which the galaxy is rotating. Okay? So the galaxy is rotating this way, it's rotating this way. In this one, it's hard to tell because you can't see the spiral arms, but it's actually rotating this way. If you look at an optical image, you can see it better. These are optical images, so you can see the dust lanes very, very clearly on the leading sides, and these are pipelines of gas inflow. Now, what does a bar do to a star in the galaxy? Imagine that I'm the center of the galaxy and there's no bar, and you are all stars moving around the center of the galaxy. You would just happily be spinning around, right? Now imagine that if all of a sudden there's a bar in the center. Then, those of you who are approaching the bar feel the greater gravitational pull because there are more stars there. And because you feel a greater pull, you start speeding up. But as you start speeding up, you have to conserve your angular momentum, so you move outwards. It's just like when you're going around a bend on a highway and you speed up. Which way do you move? You move outwards, right? So that's what happens, right? You're conserving the angular momentum. So stars will move outwards. Stars don't hit each other, right? So they will go right through the bar, and then now they go past the bar, and now the bar is pulling them back. And so they slow down. So rather than things moving in circular orbits, when you're affected in this bar radius, you're actually moving in more elliptical orbits. Okay, so that's something different that you probably didn't know. That's what a bar does. It moves stars and gas away from their regular circular orbits into elliptical orbits. And these elliptical orbits for gas start to collide. And the gas ends up hitting itself. Gas is organized in molecular clouds, and these clouds form a shock along the leading edge of the bar. And so the gas clouds run into themselves, and they basically get shocked, and they flow down towards the center of the black hole. So bars became popular in the 1990s because people thought this was a great way of feeding the monsters in the centers of galaxies. It turns out it's actually much more complicated than that, and they play a role, but it's hard to see the role. But it's a great way of redistributing the gas and the stars in the disk, which if the bar wasn't there, you wouldn't be able to do. Another thing you will notice here is as you go from these two images to this image, the bar becomes much more prominent because this is an infrared image and this is an optical image. And in the infrared, you see right through the dust. You're seeing the light goes right through the dust lanes and you only see the stars. And you can see the bar is more common because the bar is fundamentally made up of stars. And it's harder to see in these images because the dust lanes block the light. So is that clear? So that's just the basic properties of bars. They are triaxial structures. They have 3 axes, but they're very, very thin. They rotate in the same way that the galaxy does. As they go around the galaxy, they pull gas and stars that normally would go on circular orbits into elliptical orbits. That has dramatic effect on the gas. and gets gas to flow into the center. That's what I studied for my PhD thesis, but I won't talk about that today. It leads to lots of new stars forming in the center. It changes a galaxy very quickly. And so bars are very important for changing a galaxy. So the bar is outside the bulge. So if I'm looking at an edge-on galaxy, there is a bulge, but you won't be able to see the bar because the bar is thin. I'm going to try to convince you that the bar is important for understanding the age of the galaxy. Okay? So in 1972, the very first numerical models were made by Robert Kalnas. And in his initial simulations, he had 10,000 particles. And he just allowed these particles to interact with each other gravitationally and allowed that disk to rotate. And just in 2 or 3 rotations, we call it 2 or 3 dynamical timescales, the disk buckled and formed something that looked like a bar. At this time in the 1970s, they were trying to understand how stable were galaxy disks. Would they retain their integrity because they're very thin disks for the rest of their life or not? And when they saw this buckling happening, the bar forming, Kalnas called it a really troublesome instability. And they were very, very confused as to what was going on. And there was a very important paper by Oestreicher and Peebles in 1973 that basically said that any disk, if it is isolated and it's thin, so by cold, this is a jargony term, by cold we mean that most stars are moving around in a disk and not doing this, right? So if you imagine the bulge of a galaxy, the stars are triaxial, we cannot form a bar in there. So because the bar is a structure that forms in the disk of a galaxy, so the disk has to be cold. It can only form in cold parts. Once it is sufficiently massive, which means that I'm a star and I get captured in these orbits that are the lowest energy form. Well, I really, in order for me to be captured, I have to have a restoring force so I can go back and forth. So there has to be enough mass for this instability to occur in a disk. And then it has to be spinning as opposed to sort of zipping around in all different directions. And they said bars have to form as soon as a galaxy disk acquires all of these conditions. Okay, so remember that. But at that time, they knew that 1/3 of the galaxies did not have a bar. And they're like, wait, if this is the case, why do some galaxies not have a bar? And then they were like, aha, dark matter. Dark matter must stabilize galaxies against bar formation. Now, you have to remember, in the 1970s, we did not really understand dark matter. And this was one of the nails in the coffin for the existence of dark matter, because these people said the third of the galaxies where there's no bar, that bar must be kept from forming by dark matter here. It turns out they were wrong, but it took until 2002 for papers by Leah Tanasula, who's a Greek astronomer, and she works in France, and Jerry Selwood at Rutgers, to show that they were wrong, because it turns out that even in dark matter dominated galaxies, bars do form. The only difference is what the dark matter does is that it prevents the bar from forming quickly. Okay, so imagine that you have a very thin disk of gas and stars, and you're allowing it to rotate, and there's no dark matter. The bar would form right away in that galaxy, because it is a low energy state that the stars and the gas prefer to be in. But in order for me to move from this orbit into an orbit that's like this, I have to give up angular momentum and energy to something. And the way you do that is by giving it out to the outer disk of stars. You exchange angular momentum by just gravitational interactions. When you have a dark matter halo, it actually is an additional sink of energy and angular momentum, but it's in 3 dimensions. So it takes longer for it to accept that angular momentum and energy. We knew that the bars formed once a galaxy actually became mature enough. Once a galaxy acquired enough mass, became nice and quiescent and dynamically cold and spun, it should form a bar. And even in dark matter halos, we think bars will form, except they'll form later. So when I was a postdoctoral fellow, I thought, oh, this is a great marker for when a galaxy acquires the conditions to become an adult galaxy. I'm defining when a galaxy becomes adult by the fact that it is sufficiently massive, it's dynamically cold, so it's spinning in a disk, and it's isolated, and I can tell that it has acquired that conditions by looking for a bar. Okay, if it doesn't have a bar, it is not mature right now. Does that make sense? Okay. So now the beauty of astronomy is you can look back in time, right? One of the very few places you can. I wish I could look into the future, but I can look back in time at least. So the further back I look into the universe, because of the light travels at a finite time, the further back I'm looking at the age of at the universe itself. So when you look at the sun, you're not looking at the sun as it is now. You're looking at the sun as it was 8.5 minutes ago, because that's how long it took for the light to get here. When we look at the center of our Milky Way, we're looking at it. You take a photograph. That picture is the way it looked 25,000 years ago. Okay, that's just in our Milky Way. And with the Hubble Space Telescope, we can look all the way back to 10 billion light years away, 10 billion years ago. Okay? We believe the universe is 13.8 billion, 13.7 billion years old, and with Hubble we can look all the way probably to about 10 billion years ago. And so that's what we decided to do, is try to look for bars way back in time. Now other people had the same idea, and for a decade before we started doing our work, there was a lot of controversy. Some people said there are no bars present more than, this is a jargony thing, redshift greater than 0.5. I'll translate that into cosmic time. These folks published a couple of papers that said there were no bars present 5 billion years ago, looking back in time. Okay? They argued that we looked with the Hubble Deep Field that I showed you, and we just don't see them. Then I published a paper saying, well, as you look further back, you're looking at bluer and bluer light because the universe is expanding, and as the light comes towards you, it becomes redder and redder. So maybe because you're looking at, with the Hubble Space Telescope in blue light, using the Hubble Deep Field image that I showed you, you're looking at really, really blue images. Bars are easiest to see in red light. So if I'm looking, and in the ultraviolet, these bars disappear completely. So I said, well, maybe you're not seeing them, you know. And when I did my analysis, I was able to see at least some very large bars. I saw 4. Okay, so the numbers were very small. I only saw 4 large bars out of 30 galaxies. So I said, well, maybe you're not completely right. Then the next year we put the advanced camera for survey. That the second image that I showed you, the ultra deep field, and 2 papers that came out and said completely the opposite. So just from 96 to 04 in 8 years, these guys said, oh no, there are bars present all the way to 10 billion years ago, no problem. Well, so something was wrong. We can't have 3 completely different sets of things, and the reason there was this much uncertainty was because these studies were built on very small number statistics. These folks had about 80 galaxies in their study. I had the same number because I used the same data but with the infrared camera. And then these folks had about 200 galaxies. And you're trying to understand and say something about when galaxies formed out to 10 billion years ago with only 200 objects. That's not enough objects to break them down. Okay, so you needed something really, really big. And so that's what we decided to do. We did a study called Cosmos, where the previous studies, you can see the Hubble Deep Field was tiny, then people did GOODS. The last study by Jovi and Alma Green studied GEMS, but it was still a small region. You needed something enormous. So we undertook a project called Cosmos, where we observed 2 square degrees is like putting 3 by 3 moons in the sky. So this beautiful barred spiral galaxy is a very distant galaxy. And if I tried to show you what the Hubble Space Telescope saw over that 2 square degrees, my computer would have crashed. So I had to start with a ground-based image, and I took steps, zooming in, until I got to a small enough area that I could make a movie, and then we switched the resolution to a Hubble Space Telescope image, and we kept zooming in. If you were counting, there's 14 steps in it. Okay? So that's 2 to the power 14. That's the dynamic range we have. That's how much information we have in the cosmos field. And we get 2 million galaxies to study. The beauty of cosmos, lots of jargon here, but let me just give you the highlights. I know there's a lot of mixture of expertises in this audience, so let me just give you the salient points for those of you who are not scientists. Really big survey, 2 million galaxies. It's something that you can see from both the southern and northern hemisphere, so we've used every telescope to observe the same patch of the sky. So we have enormous amounts of information on this particular survey. It is the best survey to work with. So if any of you want to do a research project, all of this data is publicly available. And you can just go to the Cosmos website and get the data and the enhanced products. And what it allows us to do, because it's very deep, is we can actually study the structure of galaxies all the way out. Now, this is the question we want to answer. And again, this is again for the experts. Remember that as you look further and further back, there are 2 main things that are happening. As you look further and further back, things are getting fainter, and also the light is being redshifted, so you're looking at bluer and bluer light as you go back. In addition to that, your resolution is getting worse. Your actual resolution you know, if I can see a 1-foot thing here, I can't see a 1-foot structure way back there. So I have to take all those things into account. So ignore this, you know, detailed list of caveats, but we had to choose our galaxies very, very carefully so that we were comparing apples to apples. We were comparing the same kinds of galaxies today to the same kinds of galaxies 7 billion years ago. Okay? When you make all the different cuts to make sure that you do that carefully, you go from 2 million galaxies to 2,000. But that's still great, because now we have 10 times more galaxies to do our analysis. And the goal here for us is to try to identify what a bar looks like. And in the next 3 slides, I'm just going to give you the main result, and then I'll stop there. Okay? So you can see that you can see bars very, very easily just by your eye in this image. That's how good the Hubble Space Telescope is. This galaxy is 2 billion light years away. This galaxy is 7 billion light years away. And you can still see a bar quite well. So you would say, oh, this is easy. I can do this in one evening. 2,000 galaxies, I can say bar or not a bar, right? But the problem is your eye will fool you. Okay? Because if I asked you in this image to tell me where the rabbit is, or where the sheep is, or where the heart is, all of you can point those out, right? Or the duck, right? Because we're all natural pattern matches, right? We really can find structure like that. That's why we can see on a stain the image of Jesus, or you know, your favorite football player, or whatever, right? So you have to be very careful in astronomy not to have your eye fool you. And so what we do is we use 2 different methods of identifying galaxies. And here is how we do it. We use a computer program to fit ellipses to a single intensity contour. And in an algorithm, we try to step as the intensity decreases. So this is what we're trying to do. We are doing the ellipticity rises when you're in the center of the bar, and when you reach the end of the bar, it drops, and then the angle, the phase angle at which those ellipses are remains constant. Then they change as you go into the disk. And my student, now a professor at University of Luango, Karim Menendez del Mestre, did this really fabulous work in nearby galaxies. We understood how to do this really, really well. And we applied both techniques, your eye, which is a fantastic computer, and this technique independently to try to look at those 2,000 galaxies. Now, we were able to divide those galaxies into galaxies that were nearby and galaxies that were far away. And using both of these techniques, we identified how the number of bars changes as we look back in time. What's the number today? 2/3, right? 66%. So now I'm going to, and remember, the studies before said it could be constant or there could be none. Okay? So here's the answer. Alright, so just look at any one of these plots, doesn't matter which one, because they all show you the same pattern. On the y-axis here, it shows you the fraction of bar galaxies. Okay? Today the number is 66% up here. The x-axis here is time. We're going back and looking at the universe in steps of 1 billion years, back in time. This is what we do with just your eye. This is what you find if you just use ellipticity and position angle, that automated computer algorithm of fitting ellipses. The top and the bottom here are choosing galaxies in two different ways. So don't worry about that distinction. But what's amazing here is that 7 billion years ago, only 20% of the disk galaxies had a bar. For strong bars, it's 27% today to 9%. And for weak bars, or all the bars, it's 22%. Okay? But there are error bars there, so there's a little bit of uncertainty. But the main point to take away is only 1/3 of the galaxies were in place. Only 1/3 of, today 2/3 of all galaxies are mature. Only roughly 20% of the galaxies, only 1/3 of them were mature, 7 billion years ago. And moreover, we're able to tell you exactly in steps of 1 billion years the rate at which galaxies became mature. Right? That's the first time we've done that. And this paper took 2 years to publish because every single, what we call a selection effect, every single problem you have when you try to do this work can give you this false signature. And so we did a huge number of tests, which are in the paper, to try to make sure we weren't being misled. And the bottom line is that this is a solid result. You give it infinite time, all disk galaxies will become barred. Now, one of the things I didn't talk about is how do elliptical galaxies form. We believe that typically they form when two disk galaxies collide. And then you lose that disk galaxy because it becomes an elliptical galaxy. So this basically compares strong bars and all the bars. This shows you the previous studies, and the bottom line is the reason our work really made a lot of news, we were in 40 different countries and newspapers, is because we closed the book on this controversy by showing that all the previous data was consistent, but it was like people touching different parts of the elephant and inferring a different thing. You really needed all of the information to be able to tell exactly what was going on. So these guys were correct, that they said there are no galaxies with bars 5 billion years ago. I redid their analysis, I put error bars and huge error bars, but really they're consistent in that that number is very small. And when you have very few galaxies, you might not see any. Okay, so not unusual. Other people claim that it was constant, like this, and this point together, and then drew a straight line. They redid the analysis and they became consistent as well. There was this other study by Jogi that claimed that it was flat. She had these 2 points and she drew a straight line through it. But really it was declining. And she had the data, she just didn't interpret it correctly. What's great is a number of different studies have gone back, tried to reproduce our work, very important in science. They've all confirmed our work. Simulations have done it from scratch. They all reproduce our work. And the bottom line is that this is a really solid result. And then I knew I could leave academia and go and work in NASA headquarters. I was like, all right, I'm done, drop the mic. But it took a long time, as you saw. My first paper on this was, in the 90s when I was working on bar galaxies. And this work finished in 2008. So I started it in 2001. It took 7 years really to do this work. A second part about why this is happening. This is just really, I know I'm going to blow some people's minds because it's way too complicated to go one step further. This shows you the bar fraction. But now instead of time, what I'm showing you here is the stellar mass of the galaxies. That's also an equivalent number to the dark matter mass, or the total mass of the galaxy halo. Okay? What I'm showing you here is a line that shows you what galaxies were doing with the bar fraction 7 billion years ago. This shows you what they were doing 5 billion years ago. This shows you what they were doing 3 billion years ago. Now what's amazing here is that in the most massive galaxies, above 10 to the 11 solar masses, bars were already present at 50%. But in the low mass galaxies, at 10 to the 11, there were very few bars present. And as you go in time, so time's going this way, these lower mass galaxies started to get bars. Okay, now we've confirmed this trend with mass, with color, with the size of the bulge, and if I had an ability to measure the dark matter, I would be able to do that as well. This just tells you that not only did the universe evolve slowly as I showed you in 1 billion years, but the most massive galaxies formed first. Okay, that's amazing. It's called downsizing and normal, and there are many other papers with looking at other things that say the most massive things form first in the universe, and the lowest mass things, like the large and the small Magellanic Clouds, are just now forming their first burst of stars, really gathering momentum and strength, and they will start to become more mature galaxies as you go. Remember, this is the Hubble sequence. Okay, redshift here stands for time. Redshift greater than 3 means more than when the universe was a quarter of its age or earlier. 1 over 1 plus z, 1 over 1 plus z is the time period that you're looking back. So this is a quarter. This is looking back between 1/2 and 1/4 of the age of the universe, and this is in the last half of the universe. So what we believe is that these elliptical galaxies formed very early on. There were lots of disk galaxies colliding. They used up all the gas, they formed their stars, they're red and dead, they're just evolving. They're probably still forming, but at a lower rate. From our data, we were able to show that the most massive galaxies, because they have more angular momentum, bigger halos, they're redder, and these galaxies, we were able to show they're more massive, formed their bars first. By 7 billion years ago, half of them already had bars, which is roughly the same as today, 2/3 versus half. For astronomers, that's the same. We're very loose with numbers. There are lots of zeros. So this means that these massive galaxies were born sometime between sort of 12 billion and 10 billion years ago, because by the time you got to 7 billion years, they were already mature. So they must have been born earlier than that. And these galaxies were born much later, and they're still in the process of evolving, and most of them are starting to evolve over the last half of the age of the universe. And with another paper I did with this S4G survey, we showed that evolution is continuing even today. So the SKA, which is the square kilometer array, which is being built in South Africa and another part of it in Australia, could detect some of these galaxies, but only out to roughly half the age of the universe. And the telescope that I'm leading the study on as a program scientist, called the Origins Mission Concept Study, if it is selected, we would launch it in 2035. And it would be able to detect molecular hydrogen signatures from the beginning of time. Because it would get redshifted. There's a 17 micron and a 28 micron line that would get redshifted far infrared. So you guys have to wait till 2030. The message is, just remember, bars are common today, they weren't in the past. And they tell you how old a galaxy disk is. And so by looking back in time and figuring out the rate at which they came into existence, we're able to piece together the rate at which the Hubble sequence formed. And we were also able to tell that the most massive galaxies, the early type galaxies, had their bars first. So they formed first. And the late types formed last. That's one thing.
Wow. Thank you.